Okay, I'm going to talk a little bit about uniform continuity on a region R. And I'm only going to talk about it right now for a function of one variable. And the definition, without a whole lot of words around it, the essence of the definition is just that for any epsilon, there exists a delta such that for any x1 and x2, any two x values in the region, well, not any two, but for two x values in the region with the property that the distance between them, the absolute value of the difference, is less than delta, then the absolute value of the difference in function values is less than epsilon. Okay? And we want to explore, rather than just laying a theorem on you that function in two dimensions is if it's continuous on a closed region in two dimensions or more, then it's uniformly continuous. And that's where I want to end up. Assuming it's true. I haven't worked it through. I haven't tried to prove it. Okay? It's been 50 years since I worked through proofs of these things. But everything seems to be pretty obvious. But I want to work carefully rather than going back and consulting a textbook, making sure I'm right. I'm working through it. Okay? Just so I really understand it well enough to use the idea in this proof of the fairly simple Green's theorem in two dimensions. Okay, so anyhow, so my example, one example, I'm claiming that f of x is uniformly continuous on any finite interval. Okay, so if the interval is the form AB, where A and B are both implicitly finite, then the derivative of f prime of x magnitude of the derivative maximizes at either A or B. Okay? That is, magnitude of f prime of A is greater than the magnitude of f prime of x for any x in AB, or magnitude of f prime of B is greater than or equal, say, to magnitude of f prime of x for any x in the interval. And this comes out because the function is strictly increasing on the interval from 0 to infinity and strictly decreasing on the interval from negative infinity to 0. So it follows, well, either A is less than B, well, let's say either A is less than or equal to B, or B is less than or equal to A. Okay? And if they're equal, then that means that you have an interval that starts to the left of 0, ends up to the right of 0. And I don't want to write out all the details of this thing. You can work it out yourself. So being a little bit vague, but this is pretty obvious. Okay, and it can be proven a little more rigorously, but we're just trying to explore a little bit and not doing a necessarily rigorous proof here. Okay, so this is the case. Okay, basically, if the magnitude of A is greater than magnitude of B, then magnitude of f prime of A maximizes. And if magnitude of B is greater than magnitude of A, then it's magnitude of f prime at B. Okay, well, I'm tempted to draw a picture, but I'm not going to just yet. Okay? If the interval is an open interval, or a half open interval, then it's enclosed in a larger closed interval. And on that closed interval, it maximizes at the endpoints. So okay, so we can establish, at least this sketches out how you might prove it. So on any interval, there is some value of f prime, some value of the derivative, that's greater than at any other point, greater or equal to the value at any other point in the interval. So I'm going to say for any interval there's a value of m. Such that f prime of x is less than or equal to m. At every x in the interval. Now what's that have to do with this criterion? Well, I can say given epsilon, choose delta equal to epsilon over m. Then x2 minus x magnitude of x2 minus x1 less than delta tells you what? Well, I'm going to say, I'm going to kind of leave it to you to puzzle it over, implies that magnitude of f of x2 minus f of x1 is less than epsilon. Okay, so now I'll just raise a question. Okay, what does magnitude of x2 minus f of x2 minus f of x1 have to do with the derivative of f at points within the interval? Since the slope is bounded, for any epsilon, you can choose a delta less than epsilon over that bounded value of the slope. That meets this criterion. Okay? Another example. Okay, well, let's do one more. Let me just state one more idea. That on any infinite interval, from A to infinity, negative infinity to A, have A sub. So if you're interested, see if you can fill in the details of these proofs, or raise it to the level of a proof. Now, there's another function I want to talk about where this property that on finite intervals, uniform continuity, continuity implies uniform continuity. And I lost track of the whole form of my sentence. But there's a function that doesn't have, there are many functions that don't have this property. Okay? But any continuously differentiable function on a closed interval in which it's continuous is going to be uniformly continuous. I'm pretty sure of that. Haven't proven it. Okay? It's just part of the landscape you learn when you study mathematics. So, but still, we want to prove it. There could be exceptions. You've got to be careful. So I want to look at the function sine of 1 over x. Now this function is not defined when x equals 0. So I'll just assert and let's give this function name. We'll call this one f of x also. Magnitude of f prime of x is unbounded. There's no limit to how steep the graph of this thing can get. And if you work out the relationship between the derivative and the way this quantity and this quantity are related, which is very straightforward, but you want to work it out and see it for yourself, then it's going to be obvious that if this is unbounded, then for any interval, including 0, you're not going to be able to say this. Okay, for any interval whose endpoint is 0, it's not going to work. Now, you got to be careful. You can't have a closed interval where okay, you can have an interval open or closed on one end, but if 0 is the other end of the interval, it can't be closed at 0 because the function isn't defined at 0. Okay? So, first of all, you need to establish that this thing is unbounded. I say unbound. I said unbounded. Didn't write the rest of the word. Okay? As x goes 0, this is unbounded. So I'll say for any interval of the form 0a or a0, sine of 1 over x is not uniformly continuous. So that would be another result that you would want to establish. Okay, and that's about as far as I want to take it right now. The implication of this is, well, yeah, let's say one more thing. At any closed interval, not containing 0, sine of 1 over x is uniformly continuous. So I would suggest seeing, if you're interested, in going a little bit further into analysis, that you try to prove these things. It's just, very introductory advanced calculus and analysis, sometimes even taught in a calculus course. So, see what we can do with it.